Hello everyone and welcome to Scientific Computing and Optimization Tutorials. In this tutorial we will explain how to compute and manipulate eigenvalues and eigenvectors of matrices in C++ by using the Eigen matrix library. The Eigen matrix library is a powerful linear algebra and matrix computations library capable of solving linear systems, computing matrix decompositions, performing dense and sparse matrix operations, etc. Eigenvalues and eigenvectors are fundamental numerical analysis concepts that are very important for stability analysis of algorithms and dynamical systems. By the end of this video tutorial, you will be able to write code that's shown over here. This piece of code will define a random matrix and compute eigenvalues and eigenvectors of the defined matrix. Also, it will perform some basic operations on the computed quantities. However, before I start with explanations, I would like to mention the following. It took me a significant amount of time, energy, and planning to create this completely free video tutorial, as well as more than 350 free video tutorials that you can find on my YouTube channel. And consequently, I kindly ask you to press the like and subscribe buttons. Thanks a lot. Also, before I start with explanations, I would like to mention the following. Code developed and explained in this video tutorial is available on my GitHub page. A link to the GitHub page is given in the description below this video. Okay, let's start. This video tutorial is based on the VS Code editor for compiling the C++ code. If you're not familiar with the VS Code editor, and more generally, if you're not familiar with C++ code compilation and execution, don't worry. I created a separate video tutorial that explains how to install the VS Code editor and how to install and use the Microsoft Visual Studio C++ compiler in VS Code editor. Also, I created a separate tutorial that explains how to install the Eigen matrix library in the VS Code editor. Links to these video tutorials are given in the description below this video tutorial. From now on, I will assume that you installed the VS Code editor and the Microsoft Visual Studio C++ compiler. Under these assumptions, if you click over here on Start and if you type developer, you will see developer command prompt for VS. Run it. This is a developer environment from where we will start the VS Code editor. In this way, we will be able to use the Microsoft Visual Studio C++ compiler. The next step is to create an empty folder. For that purpose, I will go to my root folder and I will go to my codes folder. Over here, I will create a new folder and I will call it test Eigen 2. Then, let's go to that folder. Okay, and over here, we will start the VS Code editor. We will simply type code dot. And here it is. Next, let's create a new file. Let's click over here and let's click on new file. And let's call the file test.cpp. And let's create the file. Here it is. Let's type input-output stream. We need this header file. And let's type. Okay, and let's define our main function. And let's return 0. Okay, now click over here and observe what will happen over here when I try to compile the code. Click over here and we need to select the proper compiler. I will be using the Microsoft Visual Studio compiler, that is the cl.executable. Here it is, and let's see what happened. No errors. However, you can see over here, we have a new folder over here, and in this folder we have this special file. This file is very important for properly installing the Eigen matrix library. This file sets the parameters of the C++ compiler, and consequently over here we need to add a path to our Eigen C++ header files. In my case, the Eigen C++ header files are over here. And here's the path. I will simply copy and paste this path over here. But before I do that, in the previous row, I need to add comma. Then I need to type something like this. Then I need to change the path such that it looks like this. And over here, I need dash I. I stands for include. Over here, we are telling to our compiler, hey, the path to Eigen matrix library header files is over here. That is, here's the path. Next, we need to create another JSON file. To do that, we'll press Ctrl, Shift, and P. Then we will click over here. And immediately you will see this file cpp_properties.json. Again, over here we need to specify the path. Again, comma. Here's the path. And we need to make again a few adjustments to set the path in the proper format. And here it is. And we need to save this file. That's it. Let's try to compile our file and let's see what will happen. Again, everything works as it should. No errors, no problems, and of course output is completely empty. The next step is to include the necessary header files. Here are the include statements. We include vector, we include iterator, and over here we include two important Eigen C++ header files. The first one is Eigendens. This header file is used to perform dense matrix operations, and over here we include Eigenvalues. This header file is used to compute the eigenvalues and eigenvectors. And finally, we need to use the namespace std and the namespace eigen. Over here I will erase this line since I don't need it. It's just a double line. Next, let's define a few matrices. Here they are. First, we define a random matrix. It's a 3 by 3 matrix, and we will compute eigenvalues and eigenvectors of this matrix. Next, we need to define another matrix that will store the eigenvalues. Here it is. And note over here that this is a type definition. That is, this matrix XCD is a type definition for this. It's a matrix that's composed of complex numbers. It has dynamic rows and dynamic columns. This means that the rows and columns are set at the compile time. Then, we need a matrix that will be used to store the eigenvectors. Okay, let us print our random matrix. Let's see what will happen. Okay, here it is. Next, let's compute the eigenvalues and eigenvectors of our random matrix. To do that, we need to create an eigensolver object. Here it is, and we specify the name of the random matrix. Then, to compute the eigenvalues, we simply call this method eigenvalues on our eigenvalue solver, and this function will actually return a matrix, and this will be a complex matrix containing eigenvalues. To be more precise, this will actually be a vector, a column vector whose entries are the eigenvalues. To compute the eigenvectors, we will call this method called Eigenvectors. It will return a complex matrix whose columns are going to be eigenvectors. And finally over here we print the eigenvalues and we print the eigenvectors. Let's execute this code. And let's see the output. Here's the output. Let's wait a little bit. Let's analyze what happened over here. Here's our random matrix, and here are the eigenvalues. And here are the eigenvectors. Now, what is interesting over here? Over here, we can actually observe that we have complex numbers. This is very important, since eigenvalues can be complex. This entry over here, for example, is the real part, and this is the imaginary part. That is, our eigenvalue is represented by the real part and the imaginary part. Again, the real part is this part over here, and the imaginary part is here. Here's the matrix of computed eigenvectors. The eigenvectors are stored column-wise. That is, the first column is actually the eigenvector corresponding to this eigenvalue. Similarly, the second column is the eigenvector corresponding to this eigenvalue. Now, again, we can observe that eigenvectors are also complex numbers. That is, the entries of the eigenvectors are complex numbers. A large number of researchers and engineers, including myself, don't like to work with complex matrices. And consequently, it's a very good idea to learn how to extract real and imaginary parts of a complex matrix. Let's see how to do that in Eigen C++. Over here, I define two matrices, or better to say two vectors, that will be used to store real and imaginary parts of the eigenvalues. So how do we extract a real part of a matrix? For example, here's a matrix, or better to say a vector of computed eigenvalues. To extract the real part, we will simply type the name of the vector or the name of the matrix, and we will call this method real. And as the result, we will obtain either a vector or a matrix containing the real part. In the same manner, we extract the imaginary part. Once I do that, I will simply print these two matrices. And let's see the output over here. Again, it takes some time to build the code, and here it is. Let's analyze the results. Here's the vector of eigenvalues, and here's the real part, and here's the imaginary part. And we can see that the real part actually matches this part over here, and the imaginary part matches this part over here. Perfect. I've wrote a piece of code that can be used to verify the results. And here's the code. What do I do over here? Here's the main idea. Let's step back and let's look into the definition of the eigenvalue and the eigenvector. If we have a matrix A, and if we multiply this matrix A by the computed eigenvector, we will actually obtain this thing, lambda, where lambda is the eigenvalue times the eigenvector. And we can use this simple definition to verify the computations. So what's the idea? We take a random matrix and we pick one of the eigenvectors and we compute this part. This part is called test left. Then we take the same eigenvector and the corresponding eigenvalue and we compute this part over here. And this is the right part. These two parts should match each other. That is, they should be equal up to numerical precision if the eigenvector and eigenmatrix are computed precisely. Let's do that. Over here, I define two matrices, or two vectors, doesn't matter, for storing the left-hand side and the right-hand side. Now, over here, I multiply random matrix by my eigenvector. That is, I compute this part, A times V. Here's how I do that, over here. Then, I compute the right-hand side, that's a lambda, times V. I do it over here. Then I plot the left side, I plot the right side, and over here I simply plot this difference, A times V minus lambda V. Over here I print the vector on the left hand side, that is, I print the result of multiplying A and V. Over here, I print the result on the right-hand side. That is, I print the result of multiplying lambda and V. And over here, I print the difference between AV, that is the vector on the left-hand side, and the vector on the right-hand side, that is lambda V. If the eigenvalues and eigenvectors are computed accurately, then this part should be equal to this part, and this should be equal to 0. Let's verify that by compiling the code. And let's wait for the result. Here's the result. Vector on the left side, vector on the right side, and here's the error. We can see that the error is up to numerical precision. This means that our computation is accurate. That is, we were able to accurately compute the eigenvalues and eigenvectors. Next, let's learn how to manipulate eigenvalues and complex numbers. For that purpose, I wrote this piece of code. And let me explain you what's happening over here. From here, the code starts. Over here, I define a vector that will store doubled values of my original eigenvalues. Over here, I define a complex variable called eigenvalue. What do I do over here? In this for loop, I simply extract the entries of the eigenvalue matrix. I print them, that is, I print the real part, I print the imaginary part, and over here I double the eigenvalue and I store it in the vectored doubled eigenvalue vector. Over here I print the results. I use iterators to print the results. I start from the beginning of my vector. I iterate until the iterator is just before the end of my vector, and I finally increment the iterator. And I print the original eigenvalue. You can see how I do that. I'm using this function distance. This function is from the standard template library. I just need to specify the beginning iterator, the current iterator, and this function will give me the distance, that is, it will give me the current index of this for loop. And finally over here I print the value of the iterator, that is, I print the corresponding entry of this vector. Let's run this code and let's see the outcome. It will take some time, and here's the result. We can see real parts, we can see the imaginary parts of the corresponding eigenvalues, and over here I'm printing the original eigenvalue, then I'm doubling it, here's the doubled version, and I do that for the other 3 eigenvalues. Okay, that would be all for today. I hope that you like this video. If you like the videos I create, please press the like and subscribe buttons. Thanks a lot and have a nice day.